Okay, so we've got a bunch of people. So what we're going to do is go review a little bit what we did last time, and we're going to go into it in a little more detail. So let me first go here.
And by the way, the website is just becoming incredibly chock full. So you could spend a week easily on one column of one page and not be bored.
So here's what we did last time. There's a video that I'm pointing to here on the website. The tab is called Science. So this is what's called the conventional view of things as of maybe the year 2000. And we're going to fix all the errors in it. But it's called the Big Bang cosmology. So we'll just briefly review what's going on here. We had, when we got up to the year 1912, there was an astronomer in Arizona with a colleague of Percival Lowell, who was the one that saw the canals on Mars. And so he looked at 24 different, what were called nebulae. We now know that these are actually galaxies. But at that point in time, everybody thought there was just the Milky Way, and that was it. And he noticed that these 24 seemed to be redshifted. That is, when you looked at them, they were all moving away. The wavelengths were getting attenuated or pulled out. And that's making them longer, and longer wavelengths take you to the red part of the spectrum. And so all 24 of these were going away. So then in 1924, Edwin Hubble had the Mount Palomar telescope there, and he went back and looked at these, and he determined that they really were galaxies. He determined that they were typically, the Andromeda galaxy thought was 1 million light years away. It actually right now is estimated to be 2.5 million light years away. And that all of these were moving away from us. So this suggested that they all started at some common point. Now, at the same time as this is going on, we had Einstein develop what was called general relativity, where he looked at space and time being distorted by mass. And the distortion in the space and time led to what we would call gravity, that the more massive an object was, the greater the distortion in the space-time fabric in that you see. And this was experimentally verified by looking at an eclipse in 1919. And so Einstein was all over this when he saw what Hubble was doing about things moving away. So he added to his general relativity a term that would allow things to be constantly moving away, constantly repulsed. Okay. And having said that, we now go forward in time to when I picked the right time frame, 1947 is when a chap named George Gamow was looking at all this stuff, and he said, well, if everything came together, then that was the start of everything. That was what became called the Big Bang. That was in Genesis, we saw this description of let there be light, and there was light. And so isn't that amazing that our observations match with this? Unfortunately, that's not true. But then we go forward to 1963, 1964. There's two guys at Bell Laboratories that had a radio telescope, and they discovered, after cleaning the pigeon poop out of it, that they had background noise all around them. And it was determined by another group at Princeton that the background noise was probably what was called the cosmic background, microwave background, that was from this Big Bang. So they published these papers in 1964. just back to back. And this really started to take off. The guys at Bell Labs received the Nobel Prize in Physics, something like 10 years later. At the same time, in the early 60s, there were a bunch of astronomers that were noticing that stars, as they got close to the center of the Milky Way galaxy, ran into something incredibly massive, and such that the gravitational field was gigantic. And these stars, as they went around it, were doing, literally hairpin turns in the galactic scheme of things. And this led to the idea that there were what's called a black hole at the center of the Milky Way galaxy. And right now, the current estimate is that that black hole is 4 million solar masses. So the sun is one solar mass for our solar system. And again, to put it in perspective, the sun is 99% of all mass in the solar system. So every galaxy that we see out there appears to have one of these black holes in it. There's one galaxy that has a black hole that's 1 billion solar masses. So we're nowhere near that in the scheme of things. Now, what in the world are these black holes? Well, we go back in time, and we had some astronomers such as Laplace around 1800, and Laplace was doing all these observation of stars, and he wondered, geez, maybe there's a star that's so massive that light can't escape from it, that it's a star, but we can't even see it because no light can escape. But this was kind of dismissed as crazy until Einstein came up with his theory of general relativity in 1915, and right after that, in 1916, Schwarzschild made a discovery. He found that there was a solution to Einstein's equations, which was for a perfectly symmetric round mass that was literally holding in all the light so that no light could escape. And this became what we would call today a black hole. That term didn't arise until the 1980s. So here we are with this black hole. Most people dismiss this black hole because in the real world, things aren't perfectly symmetrical, they aren't perfectly round. What in the world is this guy talking about? When we go forward, though, to the early 1960s, and they actually start to measure these things, and they can't see this thing at the center of the galaxy. It's maybe 25,000 light years away from us, so we can't see it either. But the net of it is that it's attracting everything, and it's vacuuming up more and more stars. So it's getting more and more massive with every passing minute, every hour, et cetera. And the same thing is true for all of these galaxies that we see around us. Now, there's 100 billion stars, is the current estimate for how much is in the Milky Way galaxy. So this thing is only 4 million solar masses, so it has a long way to go to vacuum up everything. But it has nothing else to do in life other than vacuum up everything. So that's what it's doing. So that takes us to kind of the description, the more conventional description up to maybe 20 years ago of what's called the Big Bang. And what went with that, and you can look at this video here, which is what we did last time, is there's a second little thing, which is Escher's Angels and Devils. So if you animate this thing, let me just do that so you can see it. Well, watch what happens here. This is what the universe is made of. We start off with angels, and this is just a short animation, so it's cute. And here we see all of these angels everywhere. And again, Escher is animating. You see lots and lots of angels around the edge. That's the edge of the black hole, is what Escher is actually thinking of. And there's more and more of them, all the time getting in there, filling up everything. And then all of a sudden, just watch. You start to see darkness showing up, and you start to see demons or devils showing up, okay? So the thing just flips totally. So that's that's what we covered last time briefly. And then we went here to Roger Penrose. Roger Penrose in 1965 went back and looked at what Schwarzschild did with this black hole. And Penrose showed in 1965 that these black holes were in fact completely consistent. Even though there would be a singularity there, they had to exist. And the logic was so simple that no one could refute it. So the black holes exist according to what Penrose did. This intrigued a graduate student at Cambridge, Hawking. And so Hawking looked at this and he said, well, why don't we follow this backward in time to where everything started with this Big Bang? And that led him to say that, yeah, the Big Bang had to occur. This thing was all focused back there. So this whole thing is now called the Penrose-Hawking singularity to give it some intellectual heft or respectability. So let's just listen. Let's listen a little bit here to Penrose. I'm going to put this on. And remember, this guy is now 91. This guy is 91 years old, and you can judge for yourself that he's got a few marbles still cooking.
Talk about something before
Yes.
that singularity.
Well, I was just thinking to myself, how boring this universe is going to be. You've got this exponential expansion. This was discovered early in this century, 21st century. People discovered that these supernova exploding stars showed that the universe is actually undergoing this exponential expansion. So it's a self-similar expansion. And it seems to be a feature of this term that Einstein introduced into his cosmology for the wrong reason. He wanted a universe that was static. He put this new term into his cosmology to make it make sense. It's called the cosmological constant. And then when he got convinced that the universe had a Big Bang, he retracted it, complaining that this was his greatest blunder. The trouble is it wasn't a blunder, it was actually right. Very ironic. And so the universe seems to be behaving with this cosmological constant. Okay, so this universe is expanding and expanding. What's going to happen in the future? Well, it gets more and more boring for a while. What's the most interesting thing in the universe? Well, there's black holes. The black holes more or less gulp down entire clusters of galaxies. It'll swallow up most of our galaxy. We will run into an Andromeda galaxy's black hole. That black hole will swallow our one. They'll get bigger and bigger, and they'll basically swallow up the whole cluster of galaxies, gulp it all down, pretty well all, most of it, maybe not all, most of it. Okay, and then that'll happen there'll be just these black holes. Well, pretty boring, but still not as boring as it's going to get. It's going to get more boring because these black holes, you wait, and you wait, and you wait, and you wait an unbelievable length of time. And Hawking's black hole evaporation starts to come in. And the black holes, it's incredibly tedious, finally evaporate away. Each one goes away, disappears with a pop at the end. What could be more boring? It was boring then. Now this is really boring. There's nothing, not even black holes. The universe gets colder and colder and colder and colder. And I thought, this is very, very boring. Now that's not science, is it? But it's emotional. So I thought, who's going to be bored by this universe? Not us, we won't be around. It'll be mostly photons running around. And what do photons do? They don't get bored because it's part of relativity, you see. It's not really that they don't experience anything, that's not the point. That photons get right out to infinity without experience any time. It's the way relativity works. And this was part of what I used to do in my old days when I was looking at gravitational radiation and how things behaved in infinity. Infinity is just like another place. You can squash it down. As long as you don't have any mass in the world, infinity is just another place. The photons get there. The gravitons get there. What do they get? They run to infinity. They say, well, now I'm here. There's something on the other side, is there? The usual view is just a mathematical notion. There's nothing on the other side. That's just the boundary of it. A nice example is this beautiful series of pictures by the Dutch artist M.C. Escher. You may know them. The one's called Circle Limits. The very famous one with the angels and the devils. and you can see them crowding and crowding and crowding up to the edge. Now, the kind of geometry that these angels and devils inhabit, that's their infinity. But from our perspective, infinity is just is a place. Okay,
Sorry, can you just take a brief pause?
Yes.
And just the word you're saying, infinity is just a place. So, for the most part, infinity, sort of even just going back,
Yes,
infinity is a mathematical concept.
I think this is one
Do you
of
think
the
there's
things.
an actual physical manifest? Like, in which way does infinity ever manifest itself in our physical universe?
Well, it does in various places. You see, it's a thing that if you're not a mathematician, you think, oh, infinity, I can't think about that. Mathematicians think about infinity all the time.
Yeah.
They get used to the idea and they just play around with different kinds of infinities and it becomes no problem. But yeah, you just have to take my word for it. Now, one of the things is, you see, you take a Euclidean geometry. Well, it just keeps on going, and it goes out to infinity. Now, there's other kinds of geometry, and this is what's called hyperbolic geometry. It's a bit like Euclidean geometry, it's a little bit different. It's like what Escher was trying to describe in his Angels and Devils. And he learned about this from Coxeter. And he think that's a very nice thing. I try and represent this infinity to this kind of geometry. So it's not quite Euclidean geometry, it's a bit like it, that the angels and the devils inhabit. And their infinity, by this nice transformation, you squash their infinity down, so you can draw it as this nice circle boundary to their universe. Now, from our outside perspective, we can see their infinity as this boundary. Now, what I'm saying is that it's very like that. The infinity that we might experience, like those angels and devils in their world, can be thought of as a boundary. Now, I found this a very useful way of talking about radiation, gravitational radiation, and things like that. It was a trick, mathematical trick. So now what I'm saying is that that mathematical trick becomes real. That somehow the photons, they need to go somewhere, because from their perspective, infinity is just another place. Now, this is a difficult idea to get your mind around. So that's why one of the reasons cosmologists are finding a lot of trouble taking me seriously. But to me, it's not such a wild idea. What's on the other side of that infinity? You have to think, why am I allowed to think of this? Because photons don't have any mass. And we in physics have beautiful ways of measuring time. They're incredibly precise clocks, atomic and nuclear clocks, unbelievably precise. Why are they so precise? Because of the two most famous equations of 20th century physics. One of them is Einstein's E equals mc squared. What's that tell us? Energy and mass are equivalent. The other one is even older than that, still 20th century, only just. Max Planck, E equals h nu. Nu is a frequency, h is a constant again like c, E is energy. Energy and frequency are equivalent. Put the two together, energy and mass are equivalent, Einstein, energy and frequency are equivalent, Max Planck. Put the two together, mass and frequency are equivalent. Absolutely basic physical principle. If you have a massive entity, a massive particle, it is a clock with a very, very precise frequency. It's not, you can't directly use it, you have to scale it down. So your atomic and nuclear clocks, but that's the basic principle. You scale it down to something you can actually perceive, but it's the same principle. If you have mass, you have beautiful clocks. But the other side of that coin is, if you don't have mass, you don't have clocks. If you don't have clocks, you don't have rulers, you don't have scale.
So you don't have space and time.
You don't have a measure of the scale of space and time.
Scale
So you
of
have
space and time.
you do have the structure, what's called the conformal structure. You see, it's what the angels and devils have. If you look at the eye of the devil, no matter how close to the boundary it is, it has the same shape, but it has a different size. So you can scale up and you can scale down, but you mustn't change the shape. So it's basically the same idea, but applied to space-time now. In the very remote future, you have things which don't measure the scale, but the shape, if you like, is still there. Now that's in the remote future. Now I'm going to do the exact opposite. Now I'm going to go way back into the Big Bang. Now, as you get there, things get hotter and hotter, denser and denser. What's the universe dominated by? Particles moving around almost with the speed of light. When they get almost with the speed of light, okay, they begin to lose the mass too. They're for a completely opposite reason. They lose the sense of scale as well. So my crazy idea is the Big Bang and a remote future, they seem completely different. One is extremely dense, extremely hot. The other's very, very rarefied and very, very cold. But if you squash one down by this conformal scaling, you get the other. So although they look and feel very different, they're really almost the same. The remote future, on the other side, I'm claiming is that where do the photons go? They go into the next Big Bang. You've got to get your mind around that crazy idea.
Taking a step on the other side of the place that is infinity. Okay,
Yes.
but
So I'm saying the other side of our Big Bang, now I'm going back into the Big Bang.
back
There was the remote future of a previous eon.
previous eon.
And what I'm saying is that previous eon, there are signals coming through to us which we can see and which we do see. And these are both signals. The two main signals are to do with black holes. One of them is the collisions between black holes, and as they spiral into each other, they release a lot of energy in the form of gravitational waves. Those gravitational waves get through in a certain form into the next eon.
That's fascinating that there's some, I mean, maybe you can correct me if I'm wrong, but that means that some information can travel
Yes,
from another eon.
exactly.
That is fascinating. I mean, I've seen somewhere described sort of the discussion of the Fermi paradox. You know, that if there's intelligent life,
Yes,
being, communication immediately takes you there. So
we have
do
a
you think-
paper. I have my colleague Vahir Gurzajan, who I worked with this on these ideas for a while. We have a crazy paper on that. Yes,
so
looking at the Fermi paradox. Yes,
right. So if the universes are just cycling over and over and over, punctuated by punctuated the singularity of the Big Bang,
yes.
and then intelligent or any kind of intelligent systems can communicate through from eon to eon. Why haven't we heard anything from our alien friends?
Because we don't know how to look.
That's fundamentally the reason. Because
I don't know. You see, it's speculation. I mean, the SETI program is a reasonable thing to do, but still speculation. It's trying to say, okay, maybe not too far away was a civilization which got there first, before us, early enough that they could send us signals. But how far away would you need to go before? I mean, I don't know. We've so little knowledge about that. We haven't seen any signals yet, but it's worth looking. It's worth looking. What I'm trying to say, here's another possible place where you might look. Now you're not looking at civilizations which got there first. You're looking at those civilizations which were so successful, probably a lot more successful than we're likely to be by the looks of things, which knew how to handle their own global warming or whatever it is, and to get through it all and to live to a ripe old age in the sense of a civilization, to the extent that they could harness signals that they could propagate through for some reason of their own desires, whatever we wouldn't know, to other civilizations which might be able to pick up the signals. But what kind of signals would they be? I haven't the foggiest.
Okay, so let me just do one thing. I want to make sure that I got this thing off. A sec. Okay. So last time, I'm going to switch to what we did last time. Just give me a sec. So we had these two different creation stories. The first one was taken out of the King James Version of the Bible, and is Genesis. And the second one is a short story by Isaac Asimov in 1956, The Last Question. And so what we saw with Asimov was again and again in his short story, people were asking, how do I reverse entropy? And they kept asking this computer that was spanning the globe and then spanning many star systems and on, and it kept getting more powerful. And we saw that the computer kept saying, I don't, the question that was asked was, how do I reverse entropy? And the computer kept saying, I have insufficient information to answer the question. So they kept asking this, and finally, all of the stars are starting to wink out. Remember, this is in 1956, so Asimov had no idea about things like black holes. He knew they were theoretically possible, but they hadn't actually been observed in the center of the Milky Way galaxy. People were just starting to get there. But anyway, we get to the end, and people are now simply uploading themselves to hyperspace, which is where the computer is now living. And the last person that's there asks, how do I reverse entropy? And the computer says, I have insufficient information to answer the question. And so the person says, well, keep working on it, and uploads themselves. And now there's no one left in the universe. They're all uploaded into the computer. The computer spends some time, but of course, there's no notion of time anymore, because as we just saw, there's nothing left. There's no stars, there's no anything. It's just dark. There's still photons bouncing around and neutrinos. And then the computer realizes, I can see how to reverse entropy. So he does a demonstration, which we saw was let there be light, and there was light, okay? So that's Asimov's short story, The Last Question. So what we're gonna do is go back through why Asimov really got most of it right, okay? And we're gonna go back to our picture, which is the 26 real dimensional universe that we live in. It's symplectic in the sense that there's different subspaces that are multiplied by the square root of -1 to comparable subspaces. So there's a pairing that takes place here. I have no idea why this is the case. And the difference that we're gonna do here is Asimov had everybody uploading into the computer. So we're gonna simply look at people, which are made up of matter, and they have souls or spirits. And these appear to be, according to what Ron Cowan observed, made up of dark matter. The dark matter, matter is matter. So we're matter and we're sentient. So the dark matter is sentient, and it forms the chakras that are in us, as well as they're in all the other entities that we see around us. But the difference is that the dark matter that we're talking about actually lives forever. The atoms that we're made up of live forever, but the dark matter that we're talking about, that lives forever also. The difference is that it's in a separate subspace from the space that we live in. It's linked to us, but it's, if you will, orthogonal to where we're at. And we're going to look at some of these dimensions here, the compactified dimensions that go with the dimensions that we're in, actually are the ones that are able to control the forces that are in the universe that we're in. And that's going to be useful in a second, so you'll see. So here's Genesis. We saw this before. Here's the summary of the short story taken out of Wikipedia. I've sent this out to everybody along with the short story. You can read the short story yourself. And there we go. Let there be light, and there was light. Okay. So what are we talking about? We live over here in this 10-dimensional subspace. We have 4 dimensions for space-time. They're labeled X, Y, Z, and then time is not in meters. It has to be a length to be comparable to X, Y, and Z. So we multiply it by something which happens to be the speed of light. So that's meters per second. So now it's C times time gives us the units of meters. It just happens to be multiplied by the square root of -1. Don't ask me why. This is just what makes things work. So we have a second subspace over here, which has 4 dimensions in it. It has X, Y, Z, and ICT, but it's all multiplied by I. So now we end up with IX, IY, IZ, and now we have I times I. I is the square root of -1. So you end up with minus CT, or if you will, C, speed of light times minus T. Or in other words, time here in our dimension runs forward, it's positive, and time over here in the dark matter subspace runs negative. You have positive time and negative time. It's bad enough that we have 2 times, but they're running in opposite directions. So we'll keep that in mind. And here are these associated manifolds here that are controlling the forces and then the particles that exist in the space-time dimensions, and also over here in the dark matter subspaces. And the thing at the very bottom is synchronizing between these different things so that everything is in sync everywhere. This is what we saw with that movie on David Bohm. David Bohm was postulating that there's a pilot wave or something that we can't see. He called it a hidden variable. Or there was a French physicist called de Broglie who got the Nobel Prize in 1924 for this idea of everything that was that had a frequency, therefore it could also be a particle. And it was bizarre enough that people bought into it. And the net of it, though, is that de Broglie and Bohm both thought that there's some hidden variable, some pilot wave. And that's what Ron Cowan observed, was there's information signals flying around in these compactified subspaces that keep everything working correctly in the space-time dimensions that we're in and that the soul is in, the different spirits. Okay, so what's going on here? Right now, we're living here, and we have these chakras which make up our souls, and they're over here. So we go forward in time, and what happens is that these black holes start to vacuum up everything in sight. There's probably like one black hole left that's enormous that has vacuumed up everything. All the matter that we're talking about is here. And then what Hawking showed in the early 70s was, even though the black holes are black, that they suck in everything, they also radiate things away, and it's given a name, Hawking radiation. So over time, the black holes start to radiate. So they radiate more and more, and after a while, there's no black hole left. It radiates everything away, everything's gone. So, okay, everything is gone over here. All the matter, all the atoms that we know about are all gone. We're in the far, far, far realms of time that Penrose was talking about. And over here, all of this stuff is still alive. We still have all these sentient entities here, and they're all doing their thing. Now what Penrose was talking about, he just touched on this, was it's okay to have the universe be all quiescent and have it, be infinite, if you will, and have infinity come back on itself, because he's doing what's called something conformal. So remember, we said time is negative here. So if we get to the stage where there's nothing here but this dark matter, conceptually we could have time running backwards and pulling everything together. Remember, there still is a lot of dark matter here that hasn't gone anywhere, and that's going to come all the way back together and do a gigantic bounce. We're going to get a gigantic bounce out of this. We're not going to get a bang, though. We're going to get a bounce. And what's going to stop it, what's going to create the bounce, is that the dark matter is in, there's compartments of space. So space makes up compartments. They're very, very teeny, much teenier than you can even imagine. And they only contain 1 or 2 of these dark matter entities at any time. And the things all come back together, and the space itself, the space compartments, which again, you need 26 numbers to to talk about any point here that we're talking about, the space compartments compress. You could think of them as kind of an accordion. So we just smoosh them back together. They get smaller and smaller. When they get small enough, then everything's piling up on everything else. Then it bounces and it comes out of it. We get a gigantic bounce. This is following the Hindu tradition of having cycles of the universe. And now over time, what happens with this bounce is we create, we touched on this before, something called the Higgs boson. Okay, the Higgs boson is the entity. It simply is a scalar number, and it gives mass, actual mass, to the dark matter here. But another Higgs boson is created over here that creates the possibility of having matter. Now remember, there wasn't any matter when we did the bounce. So as it bounces out, there starts to be created enough matter so that after the bounce, we get a bang. We get what we see today, which is 13.8 billion years ago. There was this explosion that created all the stars that we see in the heavens around us. So what we see going on here is a completely consistent story that matches everything that we can see so far. Let's just go over here. The key thing about this is that it's the information that's in these Calabi-Yau manifolds, these compactified spaces, that's controlling what's going on. So what's going on is we're following a path. This is the Tao of Taoism, the way. And the way is that we go out to the ends of time, to where time doesn't exist anymore. And then we come back, we bounce back. And again, there's no notion of time because there's no anything there. It's just blackness. And it comes back and it eventually crunches down into something very small and bounces to come out of it. And what we're talking about here, what it appears is that we have an actual, in computer jargon, it would be called the data structure. And the data structure is a graph that exists in 26 dimensions. And it describes, this is information now, and it describes what each space compartment is doing. And also it describes the algorithms that evolve the space compartments and all of the matter and energy and fields that we have in the universe. So that's what it looks like, what's going on here. So let's go back to, I'm going to get out of this just a sec. And let's go look at what Ron Cowan did. Oops, went on. Just a sec. Yeah, here we go. Okay, so we didn't cover this last year, but we're covering it this year. You have to ask yourself, how in the world would Ron have ever come up with this stuff? And the answer is that the dark matter that we're talking about here, which is these immortal sentient souls, he called them mind forms, or they make up the chakras that collectively make up a soul, that they actually have some memory, a little bit of memory for, say, half a second, 3/4 of a second. So if we go back in time, they can remember what happened in that point in time. But then what they do is they go back another half a second or 3/4 of a second, and they do this again and again for billions of years as they construct the memory of what actually happened. So he's actually constructing by doing this the memory of the entities that he's dealing with here. Now, he could do it. I can't do this the basic idea that we come up with here is what's called cyclic conformal cosmology. So first of all, cyclic, the universe goes through birth, there's a life, there's a death, and then there's a rebirth. The Hindus have us at the 29th cycle in this what's going on here. I have no idea what happened to start things off. Penrose talked a little bit about this idea of conformal mapping, okay? So any mapping that's conformal preserves translation. So if I take the universe and I move it over 1 mile, I can't tell the difference. That universe is the same as the one that we're in. So it's a conformal mapping. That translation doesn't do anything to it. If I spin the universe about its center, whatever that is, it doesn't change the universe. The universe is still the same universe. And if I scale it, and this is the important thing, where even if I went out to, trillions of light years, okay, I could scale it. I could keep dividing by two, and it simply scales down the size. I keep making it smaller and smaller and smaller, and eventually I scale it back to where I have this bounce occurring. The tip off, the reason why there's a lot of problems with this stuff mathematically is because we're combining something that's discrete, which is the compartments of space, with something that is basically continuous, which is the scaling process. And at some point, I can't scale back any more than the basic smallest size of the space compartment. So that's the basic intrinsic quantum mechanical scaling that I have to deal with here, which is the way it goes. Finally, the term cosmology deals with the cosmos around us, and there's no, I don't even remember what I wrote here. There's no meaningful notion of time. Okay, when we get out there where all the black holes have gone, they've all evaporated, and there's nothing but this dark matter just floating around. This is something that appears to be lasting for literally trillions of years. Some estimates might have been 6 trillion years, except there's no notion of time till we get back to having a bounce. And then the bounce occurs, and a little later we get a bang where we have matter created. And here we are 13.8 billion years later, but we're gonna have to wait, another 6 trillion years, and everything will die out, and we're gonna go back and bounce. So these things that are called eons are incredibly long. So here we go, at birth, when we start off, there's a cloud of something with both matter and dark matter mixed up. That the matter gets generated. Remember, the matter all disappeared when the black holes all evaporated, but now we created a Higgs boson, so the matter gets created and everything is mixed up, and all of a sudden we start to end up with the hot plasma entities that finally cool off enough. And when they cool off enough, then we start to have light and dark. Let there be light. Light can propagate now through space. Before it was just all one nuclear fireball, and that starts time up. Okay, that's when time really starts up, and starts to make sense. At the death end of all this, there's just a few, or only one black hole. They're all evaporating with this Hawking radiation, giving off. It's actually information is what they're giving off. And again, there's no notion of time here. And then we go back and we have rebirth of these things again and again. We have what's called a cosmic egg to make this all happen. So this is what Ron Cowan saw. So what he actually saw was something he called the bubble torus. And as he said, almost all the memory of the previous universe, the previous eon, was erased at the big bounce. He was very emphatic that it really was a bounce and there wasn't any bang or nuclear fireball when this occurred. But there's a little bit of memory that he's getting from these entities which he called bubble torus, that survived, that made it from on the other side of the bounce to this side of the bounce, that the universe had been shrinking for a very long time, probably trillions of years. And all the space compartments that made this up had gradually just flattened out, and not only flattened, but got crushed down into the smallest that they could possibly go. So inside of each of these space compartments was a rectangular array of a large number of particles, which he called bubble tori. And we saw Charles Leadbeater and Annie Besant actually saw these in their observations too, and they called them bubble koilon. So you can, anyway, they're toruses, little donuts, and they appear to be little waves of information. That's what the information makes it from one side of the big bounce to the other side. That's what's going on. Now, this is it. Only information, let me just move this thing out of the way, is the thing that survived. And Ron took a look at this, everything, and he saw that each of these space compartments that was crunched down or flattened had 23 of these strings. He counted a few of them. He always found 23. Clearly, it's not exhaustive, but you know, it's better than nothing. And each string that he saw there of the 20, heterotic just means that the string is a closed string. It's a necklace, a closed loop. That each string was a hollow tube, and the bubble tori, or these information waves, are flowing back and forth inside this tube. And he simply saw millions upon millions, and it's undoubtedly trillions upon trillions of these. And then the strings that he's talking about were just always oscillating. So there's a dance that's taking place here. Here are some pictures he drew. He's a very good artist. So these are his pictures, and this is his text down here, which you can see when I send this thing up. But it's really a torus. There's an entity here with a hole in the middle, and so this is a cross section of it, and you can see waves going on the outside of this thing, and then it's covered. It's got all of these little information things there. And remember, these things, what Ron saw was these things are always scanning to make sure that everything is in sync, that everything isn't going anywhere. Okay, so somewhere he noticed that one of these array of 23 strings started to split in two. And it always seemed to occur whenever he looked at it between the fifth and the sixth strings, or in other words, we had 5 and 18, five strings and 18, and then 18 strings. And as soon as this happened, the way that the rules of physics work here is that the space compartment just started to rapidly expand in size. Today, we would call this inflation. So it's equivalent to a phase change. When we have something that's solid and we melt it, it typically takes up more space. It expands in the space here. So here we have space itself, and as it starts to split, there's a phase change that takes place, and it goes from a really compact thing to something that's much, much bigger. And then we end up with the space compartment having, again, 18 strings in one of them and 5 in another. And here's the same picture again, just to reinforce it. And here's his picture showing there's 5 over here and 23 over here. And so it goes. So he simply observed that in order for these, we have these 26 dimensions, but for things to be stable, according to what is governing this, the actual laws of physics, 18 of these 26 dimensions had to become compactified. So these ended up being the ones that we can't see, that we talk about, and that they turned out to be 3 different 6-dimensional subspaces, which we call these Calabi-Yau manifolds. So what we end up with here, going back to our picture, is that there's 6 dimensions compactified within the bubble torus. We had these 2 we had space-time in 4 dimensions for matter and another 4 for dark matter. And then we had each of those tied up to a 6-dimensional subspace of compactified dimensions. And finally, there was a third 6-dimensional subspace which synchronized all of the interactions so that everything, all the trains ran on time. And so it goes. So here's a different picture of he's simply trying to show what's going on with these things. And there are different helices that get formed along the way. And you end up with a winding around these things that he observed, and he was counting these things, trying to see, what was going on, but he's got these compactified dimensions in there as well. And this finally led to looking at something called the proton, which showed up as something concrete. And he saw the proton had actually 9 subquarks in it. And each subquark has 3 subquarks make up a quark. And so what he saw was there's 3 quarks. They're labeled D and U for up and down quarks, just to distinguish them. And you can see that the up and down quarks, some of them have a positive charge of typically 1/3 of an electron, and the negative charge is -2/3. So for example, if we had 2 of these here, we'd have 2 times 1/3 is 2/3, going with one that's -2/3, so we get no charge whatsoever. Whereas if we went over and looked at another one where we had one charge of 1/3 and 2 of -2/3, the charge would be -1. So you can see that the numbers magically work out. And he has pictures of these things to show what got created. He tried to play various games with these things, and he discovered that if you just took a subquark by itself, that never worked. And it always was looking around and trying to find another 8 subquarks to make up 9 subquarks in total. And so it went. But the other thing that went with it is he noticed that even when he had the 9, that they ended up in 2 hemispheres, one that had 4 and the one that had 5 in it. There was also a neutrino, which is also a torus or donut that came out of this thing. And there are 2 different types of neutrinos, matter neutrinos and dark matter or shadow matter neutrinos. Again, the dark matter is not dark, it's in a separate subspace, which is why we can't see it. So it's, it's simply orthogonal to us, is one way of saying it. And we had a subquark here for our matter, which had 10 strings in it. The 10 strings run around in circles. And then he observed a second type of dark matter or shadow matter subquark that only had 5 strings in it. So it's not nearly as energetic. And then there's a huge amount of, you can see, observations that led to, he had clusters of 19 of these tori to make up these dark matter modules here that are running around. And here they are stacked up. And then you end up with clustering together of 200 to 300 of these. And at some point, these things kick in to have sentience, to be able to actually start to form what would be called thoughts or things of that ilk. And they cluster together more and more. You had a whole honeycomb of these things. And these things just exploded and multiplied in all directions. And they end up being very much like a fern, okay? So we start off here and it looks like this. And then just in a very, very short period of time, it clusters with more and more things here. And you end up with something like this, and then you end up with something like this. So it really looks, like an incredible fern plant. And that's where he had the pictures in his book showing what the chakras look like for each of the 7 major chakras. that they're made up of this stuff, and it's incredibly convoluted. So there's various things that occurred along here. For example, there's no electrons for dark matter. The electrons only occur with matter. So therefore, all of these subquarks that we're talking about are really subnuclear, and all the combinations of these things lead to a subnuclear chemistry where they form together, and these actually sentient or living entities, they only have two states. They're either quiet, they just sit there and float in space, or they get close to something that has heat. And so, for example, it'll land on a star, or it'll land on Earth. The Earth is warm, and it'll start to come to life and start to look around and say, what can I do? And so forth. What we call dark energy is the energy that's generated from this bounce that occurred. And again, the bounce is what it is. The bounce is different than the bang. And after this bounce, what we know as matter was created. And then we go through this thing again and again. So there we have a very rapid discussion of all of this stuff. Let me see if I can get out of, we get rid of this. I'm going to close this. Now, let's stop for questions, because I threw everything at you to show you, this is stuff that Ron observed, but you could question how he observed it, of course. But the net of it is, it appears to be consistent with, a number of, shall we say, texts that were ancient. Who knows where Genesis came from, and so forth.
They think it's much older than the apparent.
Yeah, the Genesis could very well be much older.
Than the
So-
rest of them.
So, any questions out of anybody?
I have
Oh,
a
you
couple
great.
questions.
Yeah, so do I. Go ahead, Stephen.
First, what constitutes radiation that it can be emitted from a black hole, but everything else gets sucked into it?
Yeah, it appears to be information. That is, when you're talking about a black hole, you're simply thinking about things like light, or equivalently, light, because it's called a black hole, okay? But what was discovered was that the black hole by itself actually emits radiation, which I told you was called Hawking radiation. And the Hawking radiation appears to be the information that went into the black hole. It actually radiates the information out. Everything else is lost, okay? There's another little quirk to black holes, which is when you go into the black hole, there actually is a singularity in there, okay, which Penrose and other people saw. No one knows what that means, but they think it connects to another universe, or equivalently, we're in a multiverse, and our universe is only one of many, many, many universes. And so that black hole goes off to some other of these other universes.
Well, it could be like a Calabi-Yau
but-
manifold that goes off.
Well, we don't know. It's clear that there's a mathematical singularity, but beyond that, this is really where you're getting into la la land. Okay, this is, you're starting to talk to yourself and wondering what is really going on here, and so forth. So does that begin to answer your question, Steve?
Well, not really. I'm thinking, okay, Hawkins radiation. So I guess this is Marshall McLuhan, the medium is the message. If we're talking about information being radiated, it has to have some medium. And what would the medium be of this information?
Well, the title of Hawking's paper is Black Holes Have No Hair. Okay. Black holes have no hair. So you figure it out. Okay. It appears to be a thermodynamic like radiation. Okay. It's if you take what's called a black body, something that's black, and you look at how it radiates out, it'll be radiating heat, and that heat will occur at different wavelengths as you scan out through the whole spectrum there, and so you end up with that sort of thing. A similar sort of thing is there for the Hawking radiation, for a black body radiation. The point is that black holes will actually disappear. They'll radiate away enough stuff and go pop, and they'll be gone. They'll be, even the singularity going off to the other universe, wherever it is, will be gone too. But, you know.
Okay, thank you. The second question is regarding the bounce versus bang. You know, as things contract and they get hotter, eventually the concept was it contracts enough that it's overheated and explodes. I don't understand. It does that same thing, but it doesn't bang, it bounces. That part I don't grasp.
Well, I pushed Ron very hard on this, okay? I said, Ron, isn't there some heat there? And he said, no, absolutely not. There's no heat. There's this bounce that occurs. And then I pushed him to look for these Higgs bosons because I knew there was no matter. And he said, oh, there is a Higgs boson for matter being created and another Higgs boson for dark matter at the bounce. And then shortly after the bounce, that was enough to create enough matter through this Higgs boson to create the bang that you're talking about. But the bounce itself didn't have anything hot to it. He was adamant about that. And that's simply an observation he made. I can't defend it. I pushed him on it every which way.
Well, so the Higgs boson, the way you described it previously, I thought of grasp it as a mathematical concept of scaling comparable to I just being a mathematical trick. What would it be in physical terms? That there's a boson.
Yeah, the Higgs boson is a scalar. Okay, so it's not a field. Okay, it's a scalar. So when you actually do your bounce, if you will, everything is totally symmetrical at that point. Everything. So there's really no mass or anything occurring then. But when the Higgs boson kicks in, when it goes from zero to some finite mass, then all of a sudden, what you end up with is things that were massless all of a sudden have mass. That is, their mass is multiplied by the scalar number, which is due to the Higgs boson. And that's what people were looking for with this particle accelerator, where they got the Nobel Prize in 2012 for finding how big the Higgs boson was. But the point is that if the Higgs boson is zero, if it hasn't popped into existence, there's no mass for anything. Okay, just that's what Penrose was saying. There's nothing's going on. It's pretty boring.
Is that what they refer to as the God particle?
Yeah, the Higgs boson is called a God particle because it creates matter out of nothing.
And so the concept here is we have one moment where there is nothing, and the next moment the Higgs boson kicks in, and now it scales up, so you have something.
Yes, yeah. You'll see in the physics jargon they call it broken symmetry. Okay, this is where everything's symmetric. It's all crunched together, nice and clean, a nice, small universe, and then it bounces out. And as it bounces out with the Higgs boson being created, the symmetry gets broken. And all of a sudden you have these distortions called particles or called mass that show up. You also have the dark matter. Remember, for all of the discussions that we're talking about here, remember, there's 5 times as much dark matter as there is matter. Okay, that's where the action is.
Thank you.
Just a comment. So, and I need to preface this because my last physics course was in 1974. And at the same time, I was taking my English course was science fiction. So I think that's appropriate. When eternal thought expresses itself within the framework of space and time, it becomes matter. So can you say that what's inside a black hole has mass and the radiation, the information doesn't?
Well, I told you that right now in the center of the Milky Way galaxy, there's a black hole that appears to have 4 million solar masses. Okay, and that's arrived at by looking at stars that go around the center of the Milky Way, and all of a sudden they do these incredible hyperbolic turns, because something that has 4 million solar masses is really going to generate a huge gravitational pull on you. So that's where that comes from. So there really is some mass there. But the thing about black holes, or why Hawking said black holes have no hair, is the only thing that's left for them is to do this radiation of information. Okay, when you look inside the black hole, and people have done these things, there's a so-called event horizon. So if you go past the event horizon, that's it. There's no more events. Okay, or this is where you get into this nonsense. Remember, the stronger the gravitational field, the slower time goes. Okay, that's a tip off that there's something screwed up. Okay, that you implicitly you keep thinking that space and time are different than things like gravity and mass, but they're not. They're coupled together, and the coupling is intrinsic in this information that's there that makes up the walls of these space compartments, and that some incredible artist came up with a set of rules for how this whole thing evolves. It sure wasn't me, for making all this work.
So the stronger the gravitational force, the slower time goes, and the greater the speed, the slower time goes. Yeah. So for example, your brain, your head is farther away from the center of the earth than your feet. Okay, your feet are closer. So time's running faster in your feet than in your head. No wonder my feet look the way they do.
I know. I'm not defending this. I'm just saying you have to play out the consequences of these things. And that's why I'm saying Asimov was so close in doing this, okay? When he said everybody uploaded into the computer, I said, well, no, we have these souls. We each have a soul, and that's what's living there forever. And that's the thing that still has all of these things, happening. So
Bart, the observations that Cowan makes, and the manifolds and the 26 dimensions and the little pieces of discrete chunks of space and so forth. These are not laboratory observations, are they?
No, they're all the 26 dimensions is arrived at out of theoretical considerations.
Yes.
Okay, to have a self-consistent quantum theory of gravity that would allow, and that's, you need 26 dimensions to have bosons running around. Okay, that's what you need.
So
and
the
dimensions is a theoretical thing for matter. Okay, but no one, the only one that's seen this stuff apparently is Ron Cowan and Leadbeater and Besant, and they did it in the context of modern Western jargon. So there's probably other people, gurus and other ages and times that saw stuff, but they didn't use these words. These words are just metaphors.
Right, right. But their observations come from within
to
within their
describe-
heads.
Yeah,
The-
they're meditating, and
Yeah.
this is what they observe. They're focusing down, beyond the nucleus of the atom, going down to the quantization of space itself.
So
And
they've worked these theories kind of into the edges, the outer edges of what we call string theory, with an emphasis on the word theory, right?
yeah, the strings I showed you, the strings cover like the electron has 10 strings wrapped around it. So and the electron is still a donut, it's still a torus.
Mhm.
That was an observation, but as we sit here today, I know of no physics anywhere that's ever observed an electron. It's what Ron
Exactly.
Cowan observed.
Right. But yeah, the observed part is the thing that gives me pause.
Yeah,
Because
absolutely, yeah.
yeah, I can go into deep meditation and perhaps come up with something different and also interestingly appealing.
Right. And we look forward to your pictures.
But as you know, I've drawn some
Problems.
and I've written about them.
Yeah, no, Ron was a great artist, and he was very diligent about
Right.
trying to draw what he saw.
Mhm,
Okay,
mhm.
he's adamant that this is what I actually saw. But
Mhm.
what instruments did he have? This is simply him with a paper and pencil doing sketches of what he saw.
Mhm.
But
Yeah,
isn't-
I have no doubt that he saw what he saw.
Right.
I am wondering how close to physical reality what he saw actually is.
Right. Understand?
But it also has the theoretical piece that's a kind of confirmation. Because these things make a kind of logical sense.
Well, yeah, if you understand
Together.
100 years of physics studies and can synthesize it and understand the words that are being used to apply to these observations, I can't. It's beyond me.
Yeah.
Bart, I think
No.
you're closer to being able to.
Yeah, well, and that's why I drew the picture showing the 26 real dimensions, okay? And these these Calabi-Yau manifolds,
Mhm.
the physicists, argue that's really what's there, but they don't have any, they haven't built any instrumentation. I'm surprised that they haven't come up with any way to look at these chakras, okay?
Mhm.
Because those are, people, have looked at human bodies, and they do perceive, quote unquote, the 7 major chakras, okay?
Mhm.
And yet no physicist has apparently built any instrument that could actually start to detect these things. Ron Cowan went ahead and observed, all 7 chakras. He put pictures in his book. The book's available. You can get it and see it. He never spent any time on this because he said, if I spent time on this, I wouldn't spend any time on anything else. By itself, it's an incredible study.
Mhm. Mhm.
I mean,
When a
and
black
Bruce,
hole-
what do you want to add to
Yeah.
what Ron did, that Bruce, that would, I'm just trying to capture our interactions over a period of years. You're muted.
Yeah, well, one of the things that he was very excited about, I think he was talking about an electron, that he would see it moving and then it would suddenly disappear and expand to the whole universe and come back.
Right.
And when it came back, there's little bars of information appeared in the electron from what it saw when it expanded.
Right.
He was
Right,
very
so-
excited about that.
Right. So just to pick up on that, we had that double slit experiment where
Right.
we shot electrons through one slit. We just got a line of electrons on the other side of the slit. And then we had 2 slits, and all of a sudden, shooting electrons, we got an interference pattern. So all of a sudden, the electrons turned into waves, as opposed to particles. Instead of having just two lines of electron hits, we got an interference pattern, many interference patterns occurring. And so what was going on there was the electron by itself is covered with these information blocks. They're also making up the walls of these space compartments. That's what he saw. And so they're scanning out to the far reaches of the universe. But, you know, as far as we're concerned, the only thing that the electron needs to worry about is that slit that's just up ahead a little bit. Whereas if it's two slits, it turns into a wave instantly, because it propagates there and back so much faster than the speed of light. One of the things that you learn in engineering is if there's any delays in a feedback system, all hell breaks loose. So you better have everything synced completely, no delays. And this is running at the fastest speed you could possibly imagine. You know, infinite speed to the ends of the universe. But it doesn't matter what's happening at the ends of the universe, because it's only worried about the slit or the two slits. Okay, Bruce, anything else you wanted to bring up?
Well, the thing, I mean, Ron and I talked quite a bit about these experiences. The thing I picked up from it is his experiences were very vivid. He was very clear mentally about the whole experience. The other observation I sort of like to make is that when you're meditating in a deeper place like that, like there's the main experience is there's a lot of dimensions that are arising in the mind. And the whole reality of it is actually far, far more complex than anything imaginable. So one of his biggest chores was to try and articulate specific understanding and experiences to make sense out of it, which apparently you helped a lot, Bart, because you were able to kind of like guide him and ask him specific questions of what to look for and that sort of thing. Because
well,
when you really,
that's where this framework came from. Why I keep going back to that picture, that to me, there's an analogous situation here, which was in modern biology. After World War II, there was all of this activity going on in modern biology on life and what was going on with life. And they knew enough chemistry and enough biology and so forth. And so they focused on these proteins. And after a little while in the 1953, Watson and Crick discovered that there was a certain set of proteins, these deoxyribonucleic acids, or the recombinant deoxyribonucleic acids, DNA and RNA, and those controlled all the proteins. So everybody said, why are we worrying about the proteins? Let's look at DNA and RNA. And it was the control that was really where all the action went to for the last 60, 70 years in biology. Well, the same sort of thing is happening here. What's happened with physics is they focused on these particles and fields, and they got all wrapped around an axle. There's hundreds, several hundred particles now of all sorts that are out there in physics. But what's going on, they missed the point that the real question was the arena that it takes place in. That's why I keep going back to this 26-dimensional picture showing all these different dimensions, and information is in all of the different space compartments that make up everything. And that's really where all the action is. It's in the actual data structure, and in 26 dimensions, in computer science, you would call this data structure a hypergraph, okay? Because it would have 26 entities that would describe it for every space compartment. But that's just the start. There's a lot of other stuff in there for the algorithms that would show how in the world the space compartment evolves and how in the world the information processes all of the things that it picks up there in doing this scan of what's going on. Okay, and that's where the action is in the actual structure of this 26-dimensional space-time universe.
And Jesus said, in my Father's mansion, there are many rooms, and now we know how many rooms there are, 26.
Well, there's 26 dimensions, but those, remember, there's holes in those Calabi-Yau manifolds. Remember, there were 3 holes in the 6-dimensional space associated with matter, and 4 holes in that associated with dark matter. And then the synchronizing Calabi-Yau manifold has 8 holes. So 3 of the holes connect to the synchronizing space and matter. 4 of the dark matter holes connect there. And then we end up with one final hole that's in the synchronizing space. So we actually have 18 dimensions, but they're all with the holes. We only end up with 8 less than that, or 10 dimensions. And this is what we saw in the Kabbalah, that the Kabbalah had these 10 Sephiroth. That was what they sensed. They didn't have this notion of dimensions. To them, these are the higher realms, and that's what they saw as where the action was. And the Christian notion of this is we have, I look at the three things. I look at the matter subspace of 10 dimensions. Well, that's where Jesus was. I look at the dark matter subspace. Well, that's where his soul was, or where the Holy Spirit is. And then I look at the synchronizing one, or the higher realms. Well, that's where the Father is. So I can produce the Holy Trinity out of this thing. There's no notion of subspaces here. They're just words or metaphors to describe these things. Who knows if this is true? It's a picture, it's a metaphor, and so far directionally, it seems to be going where it should be going. But there's an awful lot of metrology, of measurements that haven't been made, and theories that haven't been built. But Ron actually had observations. The question is, for observations, or was he just dreaming? What was really going on there? I think he saw something, but that's he was doing it. Remember, Leadbeater and Poisson saw the same stuff, and there are other people that we saw that saw the same things as well. But of course, they're not in mainstream physics.
But there is I don't know how to put it. There's like a derived, like backwards constructed logic also that.
Well, I'm trying to.
That works out.
Yeah, I'm leaping over. There's huge leaps and bounds I'm making here, and leaving out. The only thing I know is that a good fact will kill 1,000 theories. And so Ron made these observations. If those are what he saw, then that's what I'm going to stick with to drive the theories in the right direction.
Yep. The mystics were the same way, but the bottom line is that we're all one, and we're all connected to the collective unconscious, or whatever it is. So each one of us is that little piece of information.
Yes. Yeah. And we're resonating with the greater, the Jung's, what did Jung call it? The greater collective.
The collective unconscious.
Yeah. And that's the information that's all around us in the space compartments and all the particles and everything. We're all linked. We have that. So what's in us is the same as what's above us and around us is what's going on.
We are stardust.
Yeah. Cheryl, you were trying to set something up. Did I interrupt you when you were trying to ask a question or something? You got close and then you got discouraged because I was such a windbag.
No, that's it. Marge just said it. You guys together. You guys. We could not do this without both of you.
Aw.
Because because you're one.
Well,
Yeah.
thank you. That's very sweet, Bud.
Yeah.
Thank you.
But again, we could be dead wrong, Bud.
That's the beauty about science.
So then we're all wrong, and we're all family, and we're all happy. So I'm good with this.
Yeah, these are just words. They're metaphors. You're going to take it with a grain of salt.
So I finally got my computer unmuted. That was what I was struggling for. So it's Cheryl. So the one thing I thought I could contribute tonight is I was listening to another podcast relating to how in nature everything is circles and spheres or spherical coils, and we saw that in what Ron drew. And in this podcast I was listening to, it said it helps us get less frustrated in the real world with things like a hose just wants to coil up and go crazy because it's spherical. and so the idea or the concept is because that's its nature. It's nature. And when we understand that sort of in our day-to-day world, it helps us recognize it's just being its natural thing, all the way down to this level that we can't see and barely perceive. And I thought that was kind of interesting.
Sure. Barbara, you got anything?
I'm kind of half out of it. I'm on drugs.
Okay.
Here, but thank you. I want to come back to one thing that we were kind of hitting on when we were talking in between some of the bits there. Cheryl brought up the idea of imagination. What separates people into what they look for and what they can perceive, and the fact that we often kind of put a negative connotation on imagination, but conversely, how really, really important it is. Just imagine if Ron didn't have the imagination that would kind of spur him to keep looking.
Yeah. No, that's a good point. I mean, when Ron was doing these observations, I told him, Ron, you've got to find this Higgs boson, because that would be, really, because he was fascinated with going back to this bounce. He went back to the bounce again and again. And I said, okay, so where's the Higgs boson? He started looking and he found both the matter and the dark matter Higgs boson. They both were there right after the bounce, and that's what gave mass to everything. So that to me was an exciting moment.
Absolutely.
I was making a prediction and he went ahead and did the experiment, quote unquote, to go find it.
I'd like to pipe in that I think there's a necessity to explore the philosophical distinction between imagination and vision, and whether or not there is any distinction.
Imagination and what was it, Steve?
Vision.
Vision? I thought you were saying delusion.
No, it's probably fairly close to the same thing.
Right. No,
Well, Einstein said most of his greatest insights came through his intuition.
Yeah.
And then he worked out the math, laboriously.
yeah, he would do these thought experiments, and then that would suggest to him, what was really going on. But, that's Einstein. That's, what do other people do? I mean, the problem with this stuff is, Feynman said this. He said the problem is you don't take your theory serious enough. So Einstein had his theory of general relativity, and he just thought, oh, the universe is static, so there it is. So then all of a sudden this guy Hubble comes back and says, oh no, everything's exploding, it's running away from us. So he immediately puts this constant in to make sure that things will be unstable and they're running away from one another. Okay. It wasn't something that he thought he needed. Okay. And yet that's what we would call dark energy now, which is apparently, according to Ron, this is what I pushed him on, the residual energy from the bounce. If you have things that, as you saw in that angels and devils picture, everything goes out to the edge of the universe in infinite time and then comes bouncing back, scales back in negative time, right back to a small universe and bounces. Then you end up with this, these crazy things happening.
I'd like to bring up a little bit more about Ron's experience. I'm slightly familiar with because I have my own kind of experiences. And this is what happens when meditation really goes very deep. Like the big thing is that the dimensions that arise intuitively in the mind have very vivid certainty and understanding. And it's all in a kind of a non-verbal way. And it's like, it's totally beyond any kind of reasonable explanation, but it's very concrete and vivid. And this is a part of what happens when you meditate in a very clear state. And so what, in a sense, what he was able to observe was actually really there. And but in trying to bring it into the world of normal understanding is almost impossible. But you can if you work at it. And he was bright enough to do that. But I just want to kind of like emphasize again that the deeper dimensions of the mind that you can get to through meditation are very vivid and accurate. And the great masters in meditation, you know, talk about this sort of thing all the time. And I just wanted to emphasize another quality of his experience.
Yeah, I
And
mean,
he was also a trained physicist.
yeah, Ron taught high school physics, I thought. So, but the thing about this, I pushed him on these compactified dimensions. How do you see these? And he'd look at something and say, wait a moment, there's something behind this. There's a few more dimensions behind this that I can sense. I can see them kind of piled up, or that's what compactified means, is they're curled up really tight so that it isn't easy to see them. Or he was very persistent though in trying to capture this and went back repeatedly and checked what he was seeing. Now, that one of the problems that he had was that Leadbeater and Besant made a set of observations, and he confirmed their observations independently, but he saw more than they saw. He saw, for example, what we call dark matter or shadow matter, or these mind forms, and they somehow missed it. And he saw things differently than Leadbeater and Besant, but then other people saw what he saw. So, you know, so it goes. That's all I could say.
So Herman Hesse writes about the thin gray line between genius and insanity. And I think Bruce just really brought it up, that the difference is whether or not, I think a lot more people have visions, but aren't able to articulate it. And what Ron had was his ability to express himself through his artwork. And that's what makes it real, when you can pass it on.
Well, and he did it repeatedly. I'm just showing you pictures of a few of his sketches. He had lots of sketches, but they're showing the same thing again and again. So, you know, he's consistently delusional. You know, you want to go take it, you know, but everything that he saw is consistent with modern physics. One of the problems, by the way, with string theory, why it gets so little respect, is that if we go to other areas of physics like gravitation or electromagnetism, or what's called the nuclear forces, strong force and weak force, there's a bunch of equations we can write down to describe these things. String theory has the special quality that there's exactly 0 equations.
I didn't know that.
And, you know, but I can see what the equations have to be. I documented that because they have to be relativistically correct. So they're variations of the Dirac equations, but you know, that's what I'm arguing for, and other physicists will fry me for that. so it goes. But, you know, and the other problem that string theory faces is, even though all of the major theoretical centers of physics are all packed with string theorists, there's only maybe 30 tenured chairs on planet Earth that have string theory physicists there. Okay, that's it. But there's no openings for anyone else. And the distinction that they have there is they've been able to come up with exactly 0 experiments to test string theory, other than the obvious
So
experiment.
what do you think that says, Bart?
What? Well, no,
That-
there
I
is
mean,
one.
no, but what, it's interesting, no experiments, 30 seats, that's it. And why is that not an expanding, like, why is that not growing? That's kind of a fascinating thing.
Well, it's like a luxury tax, okay? I mean, how many, you know, you have Thomas Aquinas in Paris in 1200, and he's has a whole school there trying to figure out how many angels stand on the head of a pin. You know, I don't know any experiments I could do to test that, but they had very, you know, they ate a lot of food and drank a lot of wine, and, you know, they went at it, you know, and so that's the nature of modern science, and the politics of modern science is that we have these people there. Then there's a whole pile of graduate students, okay, that are coming behind them, and they're doing this thing and that thing and the other thing. There's, you know, there's probably 1,000, you know, when the dust settles, at least on planet Earth, of these theoreticians working on string theory. But the you know, the reality of it is, the experiments that they've proposed to check out string theory are the ones I just described, such as, we'll restart the universe. Okay, how do we do that? You know, take one universe and hit
One of
the
the problems with string theory is that it dwells in a realm of the unmeasurable. Things, strings, brains, and such are so small that so far our science and our instruments have not been able to do any really good measurements. And I think maybe that might be part of the string theorists' problem in terms of getting, you know, broad recognition that they're on the right track.
Yeah, again, I want to stress, these are the brightest of the brightest, okay?
Sure.
These are not slouches by any stretch of the imagination. And the other thing is, they're dealing with, there's 2 things that are at the base of this. When we deal with these black holes, we're dealing with gravity, and which occurs over the distance of solar systems and galaxies, huge scale. And yet the black hole is on this microscopic scale, okay? It's actually really small, and ends up taking you into the realm of quantum mechanics, which is the physics that is used to describe things on the very small. So you need a theory that's consistent on the very large, gravity, but also works on the very small, which is the quantum mechanics. And that's why it's such a hard thing to come to grips with, is people haven't figured out how to do that. But what Ron saw was, it's really the quantization of space, and having these space compartments. You know, when you end up with these singularities, things that are like infinite, they don't exist in the real world that anyone's seen, okay? So that's what Ron saw, is you try to squeeze space down more and more, it gets crunched down to some basic unit, which is a space compartment that got compressed just so much. And then it bounces, then it expands out of that. And that's something that's missing, but it also requires a different way of looking at it, which is much more of a computer science view, okay? There's an intrinsic set of rules or data structures for these space compartments that make things evolve in this way. And the physicists so far, you know, we touched on this with Stephen Wolfram. Wolfram is going in this direction and is trying to describe everything through algorithms and what this means. And we'll see how far he makes it. I think Wolfram is on the right track, and he attracts incredible people, and we'll see at the end of the day. And he doesn't have tenure because he has created $100 million a year company. And so he has his own sandbox he can go play in.
You know, so we have, the really big and the really small, we have polarities, and without that, we have no growth. We have nothing new. If everything were one, we have stasis, we have no growth, we have no expansion. And it's the same, and I apologize, Bruce. I have to keep going back to this because it's the language that I'm familiar with. But Jesus was always railing against the scribes and the Pharisees. So Jesus and the mystics, they were the 30, and the rest of the physicists are the scribes and the Pharisees, and they're very comfortable. And that's what Jesus was always railing against, because they're the status quo, and if anything is outside the norm, it threatens their comfort, it threatens their existence. So that's why it's so hard to change.
Yeah.
Well, that's definitely true in science.
Yeah, in science, remember Max Planck, when he came up with the very notion of quantum and having light being quantized, people said light's a wavelength, and he said, no, it's actually a particle. And so that means if it's a wavelength, you kind of scrunch it down arbitrarily small, but you can't. It's got some intrinsic basic unit to it. You can't go any smaller than that. And he was asked, how long did it take to have your theory, your quantum theory, accepted? And he said, oh, one funeral at a time. That's the real world of physics, of that people, I mean, how could you threaten these people? And these people are not stupid, but they just get locked into these mindsets, and
there's just as much dogma, or I think more, as there is on the spiritual or the mystical side. But another thing is shamans. And Steve, I remember last year when we did this segment, Stephen shared a course that he had taken on that. This is corroborated by, like they look at microorganisms without a telescope, without a microscope, but they're seeing these, they will draw a picture of what looks like a certain organism. How are they doing that? They're in a trance, they're in some kind of altered state. Maybe they're taking some substance, and they're doing a zoom in and looking at their patients, whatever, their saliva or their blood or their skin, but they are coming up with, they can sketch the same exact organisms that scientists see with microscopes.
Yeah, remember we did cover the Yoga Sutras, and in book 3, Patanjali goes through these special senses or siddhis that you can have. And so one is clairvoyance, where you can see far in space or far in time, or clairvoyance going down into the microcosm, seeing into the very small, into the very large. And he lists, you can walk on water, you can walk through walls. All of these things are listed there. So I can argue that the proven technique is thousands of years old. Patanjali wrote this 2,000 years ago, okay? And it was oral before that. So that's the proven technique. The particle accelerators are the unproven thing. They've only been around for 50, 60 years, okay? This is 2,000-year-old science. But
I'd like to add another dimension to your list. When you listen to these great meditation masters, well, mainly they talk about, this is in Buddhism, they talk about transcending suffering and the troubles that most mankind experiences, and they're very good at it. But when they talk about the deeper mind and attaining realization of that deeper mind, so it's part of your reality and your own experience, they talk about pure perception. In other words, you see what's actually really there. And all these great masters have that reality. And that's the kind of understanding that these great masters have, and that would include Christ. He would have that reality as his normal experience. And I've met some of these masters. They're, you know, they're really super spectacular in how they understand the mind. And they instantly understand exactly what's going on in your mind and their mind. And they can talk about it. I
Yeah.
mean, it's a different dimension altogether. It's not an exploration of ideas,
Yeah.
comparing concepts. It's
Yeah,
a different.
I just view not everybody is Michael Jordan. Okay, so you end up with being able to, you know, to have this. I mean, Patanjali said these different cities, they're very interesting and so forth. But what Bruce said is much more important, to sense this incredible reality and in all 26 dimensions and all the corners of the universe. That's the richness of that phenomenon is unbelievable. This is what's going on, and the fact that these entities, these mind forms that we saw, have been there for trillions of years. What in the world are they thinking? It's the concepts they're dealing with have to be so far beyond, you know, having trillions of years to think about these things. I can't even begin to figure out how to get into kindergarten to see what they're doing. So. And Nancy, Judith, anything you want to say?
No, I'm still trying to figure it all out. It's very complex.
It's a work in progress. We're not done, you know. We're just giving you something to think about.
I guess when I think of like when you talked about the, you know, infinity, and then, you know, outside of that bounds, that boundary, and that, you know, that you go from one to the other, I guess, is that kind of the bounce? Is that
yeah, that's the bounce. Yeah.
It kind of goes over that edge, or it kind of but it's hard to conceptualize, obviously, because it's, you know, you try to put a picture to it, or you try to put something to it, and we really don't have the tools or the capacity to fully
Yeah,
conceive.
you know, it's clear, you know, if you're thinking of something that gets crunched down, then you immediately think, well, then there's something outside it, but there isn't anything outside it. This is the entire universe that you're crunching down. Okay, so what do you mean there's something outside it? So it could be the universe is in, for example, a ball, and that's why the picture of the angels and devils is so correct. Is that everything is inside there? So when you try and reach the edges, there is no edge to reach. It just gets smaller and smaller, and then it bounces out of that. You know, there's different metaphors to try and describe these things.
Well, but also, I guess, in my mind, it's like okay, so it's a ball. It's, you know, that's the whole universe. But to me, it's like, well, it could be the ball in some kid's hand in another realm, right? So no, it's not. It's not everything. Like, can you ever get to everything? There's always got to be something more.
Well, that's what we said. We said that there could very well be multiple universes or multiverses. So
Or it could loop back on itself.
Yeah, we're bouncing around in this one, but there's a gazillion more that are doing the same thing. Maybe they're all interconnected. You know,
the dandruff on some guy's head.
yeah, absolutely. No, you know, it's called what's the phrase? It's called
shrinking reality.
No.
Is that? But I was fascinated by that actually in nursery school, and my mother said, "Oh my God, she's thinking about shrinking reality already."
You know, I think one of the things maybe, Nancy, is that we're all, you know, most of us our world is two-dimensional mostly. And so we don't have to know the definition of space and time. We just know it because our experience is always in those realms. And infinity is more conceptual to us because we don't reference it that frequently. We don't use it on our real world. And I think that that is one of the reasons why we have a hard time grasping it.
Right.
Yeah.
Good point.
And mathematicians will actually talk about different infinities.
Yeah,
You know, what does that even mean? But to them, it's very clear and very vivid for them that there's these different species of infinity
Yeah.
that can be within each other or alongside each other.
So, your takeaway could be Genesis was right. It just left out a few details.
It's a little simplistic to me.
Well, Genesis was really compressed, like a couple billion years into 7 days. That's compaction.
Right. Right.
If you look at the Kabbalistic footnotes, there's a lot more to it.
Yeah.
It's a lot deeper and it's really interesting.
Yeah, there's a huge amount of in the Kabbalah, the meditation that these mystics did to come up. There's, all of which is really just now coming to being popularized. Okay.
Well, they're just revealing it.
Yeah. Yeah.
So I should ask Mom because I don't remember what is what's the story in Urantia?
Urantia?
Yeah.
That's Urantia, Urantia.
Yeah.
I think she's asking Judith something.
Oh, Judith, you're muted. Judith, you're muted. Hold on.
Okay. Well,
Sorry.
do it again.
Unmute. Unmute. Go ahead. Judith, unmute.
I am unmuted.
Okay,
There
great.
you go.
Great.
In the Urantia book, the universe is multi-layered. And we, as a planet, or our Milky Way, is on the outskirts of it. And as you gain, let's say, intelligence or
Experience.
spirituality, you move further in to the universe, away from the edge. But we're on the edge and we're way down.
Yeah, but I'm asking, what about the creation story? It's much more. I don't know. I don't have mine anymore. I'll have to look at it when I'm there.
What is this from?
The book of Urantia.
Yeah. That's why I spelled it. So
You'll have to look it up.
Urantia. Yeah.
Supposedly the Urantia book is what, like, Einstein got some of his theories out of. Who else? Who's like some heavy hitters until it's like it's just much more. It's got Christ, the story of Christ in there too, but it's a little bit more science fiction. Like it includes a bit more. How do I say this? Like we're not the only, that there's an interface between us and elsewhere within the universe, and that's how we kind of came about or evolved, and it just helps make it seem a bit more. I mean, it's a little far-fetched, but it's certainly not outside of the realm of
Well, this is far-fetched. I mean,
there's a notion of evolution underlying all this. So, and
Right.
change,
Right.
that everything is changing all the time.
right,
It's very dynamic.
right.
This talks about the central and super universes. Then it talks about the local universes. and then the history of Urantia, which is technically our planet.
Earth, right, Earth.
And then it goes into the life and the teachings of Jesus. And they're papers, and there's 196 papers or more. And not, I've read it 3 times, but I'm getting to the age where I don't remember everything.
Well, again, they're metaphors. So here we talked about these dimensions. So we talked about the 4 dimensions of space-time, but then we talked about the higher realms. You know, these other dimensions above it, where the real action takes place. Okay, and so it goes. So, and the fact that you thought there's 196 is interesting, since that's how many sutras there are in the Yoga Sutras of Patanjali.
Oh,
Yeah.
okay.
Right, wow.
So
So the-
anyway,
We have to get a copy.
yeah, we'll go
Yeah.
track it down. Thank you for the pointer.
Yeah.
Eh,
definitely.
I'm just looking at the time, so I'm sensitive. Is there anything
Yeah.
else anyone wants to bring up? Yeah, go
Real-
ahead.
real quick, every one of our books of wisdom is just an attempt to articulate what you can't put into words anyway.
Mhm.
Carl Sagan, it's a metaphor, it's a like and as, Carl Sagan talked about this, that the language of science is math. So we're always using metaphors like and as, so we,
well, Yeah,
we just
that's a good point. To see, when I keep talking about these data structures in 26 dimensions, these hypergraphs that describe what's going on, it's just articulating that math is really the natural language that's describing all this stuff.
Mhm.
That's why we sense that that's what's going on. But I think what Bruce said, that you're saying this intrinsic reality, which is so rich and multifaceted, and it evolves, is words don't do the job. You have to actually walk the walk, and you can't just talk it. Words don't do it.
Mhm.
But they point toward things.
Yeah. Yeah, but they can also mislead you.
Mhm.
Well, they
You know.
reduce it, everything. They're
yeah.
always reductive, but
Yeah, it's almost right, so it's wrong. Anyway, let's call it a night. And thanks everybody for participating. And I know this was a heavy jolt, but cosmology is what it is. It's when you deal with these sorts of questions, there's it's going down the rabbit hole in Alice in Wonderland.
I just want to say the ancient Greeks considered astronomy to be the theoretical branch, and astrology was the practical branch. Because that
Yeah.
was like applied
Applied
astronomy that they thought you could just see. It was just kind of self-evident. It was much simpler
Yeah.
than these theoretical projections of possibilities.
Right.
They thought that was a lot more abstract and theoretical.
Yeah. Okay,
So on that note,
we'll let everybody go. Have a good weekend, everything.
thank
And
you, everybody.
we'll send you the recording and some
Okay.
handouts. Have a good. Okay,
good
bye-bye.
night, everybody be well.